All right. The test, guys, on Monday will have two problems only. One will be a fire pump that could have either a transformer or no transformer. And the other one will be an adjustable circuit breaker. Cool? So I'm going to go over the fire pump, two examples for the fire pump, one with a transformer and one without transformer. These are two examples. And at the end, I'm going to do an adjustable circuit breaker calculation. But on the test, there'll only be two. Cool? So you guys have that sheet in front of you? Everybody have that sheet? So this is a fire pump, Adam. Make sure you guys have the calculation handy for you. A fire pump without transformer. Code letter J, code letter K, 30 horsepower for the fire pump and 7.5 for the 480 for the jockey pump. Everybody understand what we're doing? Cool? All right, let's go ahead and do it. The first thing we need to do, and I have the calculation for you guys, is find all these, 10 things for this one, 10 things. We need to find the feeders and the branch circuits and the controllers and the auto transfer switch and the overclock protection device for the whole system, right? Everybody can see that? The system that we need to find. All right, so Adam, the first thing we need to do, my friend, is go find the full load current, fire pump full load current. To find the branch circuit, you need to find the full load current. I went and I found the full load current for you guys. This is a 40 amp. And then you multiply the 40 amp by, because it's continuous duty, by 1.25, that'll get you 50 amps. Then you take your 50 amps, at 310 V16, 75-degree column, and that will give you three conductors, gentlemen and ladies, and number 8 RHW. Straightforward. You guys have, I'm not going too fast because you already have this information in front of you, right? So, but that's basically how we calculate the conductors. Mistake number 1, Karen, is not to know which table to go to. For the test, guys, bring the cheat sheet with you. There's a lot of calculation. Bring your cheat sheet. Adam, good? Next. All right, let's go to the next one. The jockey pump. The jockey pump, no difference, guys. Find the full load current, 11 amps. Multiply 11 by 1.25. That will get you 14 amps. And take your 14 amps to 310.15 V16. 310.15. This is 310.15 V16. Table 310.15 V16. That will give you 3 conductors and number 12. Why do we use number 12, Adam? Commercial industrial, you don't want to use this than number 12, right? That's your minimum. Is this code? No. Industry standard, yes. Next. Okay, now the second thing is a controller. For the controller, do me a favor. DeWalt, everybody knows where to go to DeWalt to 6-4. Based on the horsepower and the voltage, 30 horsepower, 480. This baby should be NEMA 3. You guys that one? For the jockey pump, based on the horsepower, 4.5, 480. 4.5 horsepower, 480. 3-phase, of course. This will be a NEMA 1. This will be a NEMA 1. No overload. No overload. Cool? You guys have a copy of this, so you shouldn't be too fast. So that's straightforward, the NEMAs. Controller feeder, Adam, the feeder that feeds the controller, you guys have the sheet in front of you. The controller that feeds the feeder, the only challenge is you have to add them up and multiply them by 1.25, so that will give me 64 amps. And then you take your 64 amps to 310.15 V16. That'll get you 3 conductors and number 6. 3 conductors, number 6, RHW. Straightforward, guys, we have done it. Are you guys filling these little numbers? ATS, no difference. You take the 40, multiply it by, add it to 11, multiply by 1.25, get 64. Take your 64. This time you take your 64, guys, to where? DeWalt. You take it to DeWalt 3-12, and that will get you an 100 amp auto transfer switch, 100 amp auto transfer switch, right? So if you don't ace it, Matt, we're going to take it outside, you and I, and drink coffee. Really, no, I mean, step by step, right? It's not going to be a difference. And the good news is I don't have a problem with you guys having the cheat sheet. All right, conductors from the service. We'll go to conductors from the service. We said same as step number 5, so that will be 6, 3 conductors number 6. Conductors from the generator, same thing. 3 conductors number 6, gentlemen. No difference. No difference. Shall we? So the same calculation, no difference. Now we're going to go to the overcome protection device. And this is a little bit funny, the overcome protection device. We have to find the locked rotor current for this motor. Remember, there is a K and a J for these. 430.7B. You will find that for this one for locked rotor current for the fire pump is 8.99, the multiplier. You multiply it by 30 horsepower. You plug it in and you got yourself 324 amps, gentlemen. That's a locked rotor current. The jockey pump is 7.99. That's the factor from the table. You do your math for the jockey pump, 7.5. That gets you 72 amps. 72 amps. Then you take your, add them up, you 324 plus 72, and that will get you a healthy 396. 396. Then you take your 396 to 240, that's 60, and that'll get you 400. You go up to 400 amp. So your circuit breaker is going to be 400 amp. Now, how easy that is. I bet you my grandma would do that. She doesn't know English though, that's a problem. Might have to do it, translate a little bit. Does that make sense, guys? See, it's straightforward. Matt, make sure you have the, I don't want you guys to have the example in front of you, but please have that cheat sheet. Okay, overcome protection device from the generator side. From the generator side, guys, we multiply by 2.5 from the NEC code book. So you take 40, multiplied by 2.5, that gets you 100 amp. As if we have just hit the jackpot, 100 amp will give me 100 amp. So remember, if it's not standard, you go up though. Then you take your 100 amp and add to it the full load current. That'll give you 111 amps. You take your 111 amps to 240.6, go down because it's a feeder that will bring you down to 110. So you're from the generator side, you will have 110 amp max. Can I emphasize the word Derek max because you can use this and that. That's it. Is that easy? The next one, guys, we're going to do one with a transformer. We're going to do one with a transformer. Shall we? Am I going too fast? Karen, Matt, no? We've done it the other day, and this is just, you guys have a cheat sheet. You have the stuff in front of you, so if that's why I like to make copies of them. It expedites the process for you. All right, let's take the second example, gentlemen. The second example, Adam, is same thing, jockey pump with a fire pump connected through via a controller and an a transformer and an auto transfer switch. And we need to size the system. We need to size the feeders for the auto transformer from the generator, from the utility, out of the auto transfer switch to the transformer, out of that transformer to the controller, for branch circuits between the controller and the pumps. Code letter RS and horsepower 3 and 75. So let's go ahead and do that. Straightforward, Karen. We need to find the full load current, which is 211 for this boy, 430.250. Remember, it's a 2.8 system. Then, since it's continuous load, Adam, we multiply by 1.25. That'll get you 264. 264. And then you take the 264 to 310.15 B16, 75-degree column. And that will get you a healthy conductor. How many conductors? Always three-phase, 3 conductors, guys. That's the beauty of three-phase. 3 conductors, and the size is 300 KCM RHW. No gimmicks. Why not 4? The beauty of three-phase, guys, is we don't need a neutral. Typically, Derek, if you have to, if somebody tell you three-phase load, do you need three conductors or four conductors? The default is three. The default is three. A neutral is only needed if you need it. You put a neutral if you need it. For example, if you have a panel, three-phase panel, you need a three-phase, and do you need a neutral? Well, are you connecting anything to the neutral, Chad? Yes, lights, for example. Then you need neutral. Now this is a pump. They're all running at 480. Well, what am I going to connect to the neutral? Nothing. Now Adam might say, how about a control relay, Chad? If you want to do some control, all right? You know what they do? They take two phases and a little transformer. They transform the two phases from two phases, the power, and make it 120, little tiny little control transformer, and they use it to control the system. So they don't need neutral. They create a new through a transformer. They create a new system. Okay, jockey pump, guys, no difference. For the jockey pump, 3 horsepower, that gets you a healthy 10.6. A 10.6 multiplied by 1.2 give you 13 amps. At 13 amps, Adam, will 310.15 B16 could give you actually a number 14, but please, on the test, don't use this the number 12. Could we have gone, if you go to the table, guys, it will tell you 14. But commercial industrial 14 is dwelling. You start pulling commercial industrial, drop that number 14. There's voltage drop issues and there's other issues. Cool? All right, fire pump. Now the controller. Controller goes straightforward. You take the 75 horsepower at 208 and the wall 6-4, and this will get you an EMA 5. Same thing for the jockey pump, 3 horsepower 208, the wall, that will get you an EMA 0. That's straightforward from the, make sure where you go, right? Just make sure where you go in these, no gimmicks, nothing. So 5 and 0. Controller feeder. The controller feeder, my friends, that's the feeder coming to the controller. You take the full load current of the two pumps, add them up. When you add them up, 277 amps. When you add them up, then you would take 277 amps, take it to 310.15 B16. There's my amps. And that will give you a healthy 3-conductor size 300. Didn't change. 300 kcm. Did not change a whole lot. We're still pulling 300. We pulled 300. Because the other pump was small enough that didn't make a difference in terms of the feeder. 300 kcm. No gimmicks, nothing, gentlemen. That's your number 5. Cool? Okay, transformer. Sizing the transformer, because we have transformer here. You take the 211 and plus 10.6, and then that will get you same thing, 277 amps. Then you take the 277 amps multiplied by the whole system here. That will get you 9.9 kVA. And if you take the 9.9 kVA to the 177, you landed a healthy, very nice. This is when I like it. Look at that. You want 9.99 and you end up with 100. Perfect. I don't like it when like you need 75 and the next standard is what? 100. Oh my God. I mean, so it's nice when your load is kind of close, very close to your system. That's, guys, when sometimes if the load is way too far from a standard, you know what the engineers do? They go down. But for the test, you need to use your judgment. If the load is, say, 75 and the next standard transformer is 100 or 60, a lot of engineers will go down to 60, knowing that the load is not, there's a lot of diversity in the load. For the test, please follow these procedures. Okay, now this is where we diverged a little bit from what we did because we multiplied by 1.25. So we've got that transformer. Okay, primary overcome protection device number 7. For primary overcome protection device, my friends, based on the lock total current of the two of them, you need to go find, I believe this is 17.99. Plug them into this formula. That will get you a healthy, wow, 3,749 for 3,749. The lock total current for the jockey pump, the multiplier is 15.99. Plug it into this formula. It'll get you one. What's my horsepower? No horsepower? 3. How much? Should be 3. This one? Yeah. Can you do the math again? Maybe I did. Can somebody use the math? Thank you. So the first one is 7.5 is right? Yep, 7.5. Can somebody check the math, will you?
Yeah, 133.3. Yeah, the math is ready.
Oh, but that one I forgot to. Thank you.
Yep.
3. And then add it up. 3,749 and 133. That'll get you 3,882. Take him to the next level, which is a 3,882. Now we're going to multiply them by the voltage ratio. Everybody understand what we're doing? We'll multiply them by the voltage ratio because we're looking at the primary. We have to multiply by the voltage ratio like we said the other day. That will drop it down to 168.2. Matt, do you see how beautiful that, when you raise the voltage, how much you went from almost 4,000 amp down to 1,600 amp just by raising the voltage. Okay, now then you go to the primary side to 1682. Take it to 240.6, guys. And that will get you a healthy 2 grams. 2,000 amp. Now, if you have an adjustable circuit breaker, Adam, you might be able to adjust it to 700, and that's okay. Did you guys hear me? The next standard non-adjustable is 2,000. But if we have an adjustable circuit breaker like this guy, definitely you can go from 1682 down to 700. That would be 700. The worst scenario, if you have a fuse, which is non-adjustable, then that's what you get. Okay. Shall we go to the next one? The next one, guys, is the primary conductor. Here's my 100. Find the full load current for the 100 in the primary side, Adam. Get you 120. Do me a favor. Here's one step I don't want to use. Direct, I don't want to use this step. I don't want to multiply again by 1.25. Can you guys cross this step? I don't want to multiply by 1.25 like I did. I used to. You know why I didn't multiply? Because when we sized the transformer, we already multiplied by 1.25, you remember? So I'll take the 120. I need somebody to help it because that's, take 120, take it to table 310.15 P16.
You get the 100 kVA.
The size of a transformer. Right here. Remember we came up with a size of a transformer. Now we're on the primary side. Right? Now we size the transformer, 100 kVA. Now we need to go and we size our computation device on the primary side. Number 8 is sizing the conductor, right? For 120, what's the amp for 120? Adam, did you come? Number 1? Do I have a second? Number 1 or number 1 not? Number 1. I'd like to have a second too. Okay, 120 is number 1.
Shouldn't it be 277 times 4.25 and then divided by, yeah.
We're on the primary side.
Well, no, go back to number 6.
Number 6, okay, let's go to number 6. All right?
277 times
That's how you find the KVA.
Yeah, at 208, and you're in that side, so wouldn't it be at 99, and then you go over to the KVA, or you're just using the KVA reading?
Yes.
No.
We look at the first column. We're not looking at amps, we're looking at KVA. You have 99.9 KVA. What's the next standard?
Oh, okay. I was going.
By amps.
Yeah, I was going with the amps and the full load. So.
Yeah, that's all right. You're looking at KVA here. Got it? Okay, so size. Number one, I verified it. So that's number one. For the ATS, guys, the same thing. For my ATS, I don't want to multiply 10 gigs raised to 1.25 again. So I want to size it for 120 amps, which is die primary. You take 120 amps, you take it to the wall, that'll give you 200 amps, right? Derek, 200 amps? 200 amps. Can you guys cross? There's a multiplication by 1.25. Don't multiply by 1.25 again. It's too many up. So that's what you get. The asterisk here. So that's my ATS. Make sense? Now we're gonna go to the rest of them, guys. Is conductor from the main. Where did I get number 8? Same as number 8, yeah. Conductor from the main, same as number 8. And what was number 8, Adam? 1. Number 1. And conductor from the generator, same as number 8, which is also 1. So these are exactly 1, 1, 1. No need to. Number 11. What else? Did we do all of them? We still have number 12. These are straightforward. Overclock protection device from the service side, same as 7, which is 200, right? Is that what we came up, 200 amp? Then conductors from the generator side. Is it 2,000? Oh, where is 200, Chad? Have I been drinking other than coffee? Okay. Okay, same as from the generator side, based on the lock total current, right? Yep. 1,000 amp. Based on the overclock protection device from the gen side, guys, we'll take the 120. Yep, here's my 120 amp. We're going to multiply it by what's transformer 1.25, 120, 1.25 amp get you 150 amp. You take the 150 amp to 240.68, that will get you also 150 amp. So on the generator side, you put 150 amp circuit breaker. And that's, I believe, what we did last time. Okay. You okay with that? Straightforward. Let's do the last one, guys. Any question about the fire pumps? Really straightforward, no gimmicks. The second question on the test, Adam, will get you a big, fat, fluffy, adjustable circuit breaker. This is the same picture that we guys looked at. Look at this. We have a frame size of 4,000, sensor 300, plug 2,000. The settings are long time pickup, long time delay, short time pickup, short time delay, instantaneous, and a ground. And I'll give you the settings, and you guys need to find the stuff for me. Okay, here's the example. Here's what the example is going to be. Find the following. So they will tell you find the following for an adjustable circuit breaker. Now, Matt, the frame is 4,000, the sensor is 3,000, and the plug is 2,000. And I would like you, and the settings, I decided to put the setting as 0.7. Can you see that? I have a 0.7 setting. And I need to find the settings in amps. So, settings in amps, what do you guys do? Like we did before. You take the settings, 0.7, 0.7, multiply it by the plug, right? What's my plug? It says by the plug. So you need to go by 2,000. And that baby will be 1400 amp. For the test, Adam, can you please write the formula for you to find the long time pickup in amp? You multiply the settings, long time pickup setting by plug, not frame, not sensor. Write it down, right? So when you multiply by the plug, not the sensor, not the frame. Okay? Then size the conductor, gentlemen. The second thing that I will ask you to size is size the conductor. I'll be asking you to size the conductor. So you're going to take the 400, so the long time pickup is 400. You're going to take the 1400 here, 1400, I divide it to parallel 5. So that will give me 280 amp. If you guys go to 240 table, 310 and 15 B16, 75 degree column, you have 5 sets of how many conductors? Let's just say, for the sake of the argument, guys, 4 conductors. Each one of them is 300 kcm. 300 kcm. THHN. THHN. Now, if you parallel 6 sets, would it be wrong on the test, guys? Paralleling is when you parallel, you want to hover around 400. Adam might parallel 4 sets and end up with, say, 500 kcm conductor, and that's fine. So that's how you size your conductor. The most important thing, guys, is sizing the conductor based on the long time pickup. So, Derek, on the test, question number 1 will be find the long time pickup in amps. Question number 2 will be find the conductor size in AWG or KCM. So that's what you're going to do. All right, the third question would be, or this case is the second here, short time pickup in amps. I am telling you, I'm doing setup, I'm setting my short time pickup at 10. The formula is setup times long time pickup. You take the setup that you have multiplied by long time pickup. So Adam, my setup for this one was 10. Multiplied by my pickup in amps was 1400, and that will give you a healthy 14K, 14,000 amps. Can you guys see that? That's your short time pickup, which basically your ground fault. When it sees a ground fault, that amount, it's going to pick up. Okay, question number 3. Instantaneous pickup settings at 20. The formula that you're going to write and bring with you, settings to find it, instantaneous settings times plug in amps. Settings times a plug. What's your plug? So my settings are 20 multiplied by my plug. My plug is 200. Sorry, 2,000. That will get you 40K. 40 kiloamp. How easy that is. And then the last thing, Adam, is instantaneous time to open circuit breaker. The instantaneous time, I put my instantaneous time settings at 10. I dialed it to 10. Can you find the it's 10 cycles, not 10 seconds. If I dial it up to 10 cycles, how many seconds is 10 cycles? The question, really the easy thing is, can you convert a cycle to a second? What is the 10 cycles in seconds? So piece of cake, you take your 10 and divide it by how much? Gentlemen, 60, because there's 60 cycles in a second. If you have 10 seconds, how many cycles is 10 seconds? How many seconds is 10 cycles? So you take the number of cycles divided by the 60, because there's 60 cycles in a second, and that will get you a healthy 0.167. 0.167 second. Second. Gentlemen, you have just aced test number 4. I'm gonna give you 5 minutes. I'll go over the theory, shall we? And then I'll let you monkey around with the project.